Hello, everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode 29, where today we have a very highly anticipated episode, at least on our part.
That's right.
Quantum Mechanics Part 2.
Quantum Mechanics Part 2. We've been itching. Just itching to talk about this topic.
There's some really crazy things that we can talk about in this. Also, one thing I do want to mention just before we get right into the podcast is that on the last episode, I mentioned that we're going to be changing our schedule to Fridays at 10. So yeah, just scratch that. We're going to move it back to Saturday because we found out that with school starting, it's basically impossible to record anytime during the weekday. And the only day that both of us are available is Friday. So the only option is basically to post on Saturday. So that's right. What we're going to stick with.
So yeah, we're just going to stick to the normal schedule. You know, we've been posting Saturday at 10 a.m. since pretty much the beginning. So I guess we'll just keep that.
Okay.
So yeah, we have started. Okay. This is the first actual podcast that we record during the actual school year.
Yeah,
because the last two that we recorded, school started, but it wasn't it only started for 2 days, so we weren't actually
it didn't really start when we did this.
That's right, but now we are 3 weeks later.
Yep.
Has it been 3 weeks?
Actually, because the podcast that we recorded, the one last week, the one with Matthew Cater, and the one before that, we actually recorded on the same day. 2 weeks ago. I think we mentioned this in a previous podcast.
Yeah, we did.
And so that's basically why we've not really recorded during school. So here we are.
All right. So now, as you know, we both have quantum mechanics as a course this semester.
Yep.
And we have learned some quite interesting things, some postulates here and there, some mathematics, definitely. So yeah, we're just going to talk about quantum mechanics and expand on the things we've already talked about in our first episode. And on top of that,
episode, I think we were pretty general, weren't very deep into it. I think this episode we're going to go a little bit deeper into the realm of quantum mechanics.
To be honest, I don't really remember what we talked about on the first episode.
That was a very long time ago.
That was 2-3 months ago, maybe. Yeah. Anyways,
I mean, 3 months in school terms, especially when you learn so much every single day, it's pretty crazy. It's pretty crazy. Yeah.
So I'm guessing last time we talked about probability density and double slit experiments, things like that. Anyways, so let's kick off this episode by talking about something I know we didn't talk about last time, which is spin. Because we had no idea what spin was. I mean, technically, we still don't.
Did. I mean, okay, to be honest, we have a decent idea of what spin is. But I mean, if you we don't know it to the level of probably our professor. Yeah. Not even close.
So, I mean, it takes a lot of just deep thinking and analyzing mathematically, because it's not a physical I don't know how I'm trying to explain this, because I forget if this was a pre-lecture video or something like that for our quantum course, but basically our professor said that if you ask around the physics community, there's not really a general consensus on the size of an electron. Some people say that the size of the electron is the size of the de Broglie wavelength. Some people say that it's the size of the cloud of the around the nucleus. Yep. Some people say that it's just a point particle, and so it means nothing to say that the electron has a size. So to say that an electron can have spin doesn't really translate to anything physical. Right?
It's basically an inherent property of the electron. It's kind of analogous to angular momentum, when we think of that.
No, yeah, basically it is angular momentum, right? So you can have up spin or down spin, right? I mean, this is this is like the simplest form, right? There are more complicated systems of spin, but if you have what we call a 1/2 spin system, is basically there's two options, right? You can either have upspin or downspin when you run it through an analyzer, right?
So what we mean by half spin systems is, so a half spin particle is what's commonly referred to as a fermion. And if you guys, I think we've definitely spoken about the standard model of particle physics before in one of the, I do not remember which episode, but one of the episodes for sure. And we did speak about fermions, or at least I think I touched on it a little bit, or at least I hope I did, where fermions are basically the particles we see in everyday nature. So our most basic fundamental particles are fermions, and those are all half spin systems, or those particles are what we call as half spin. So we're going to get a little bit into what half spin is in a bit, but now we're just trying to bang the idea home of what spin really is, and how in our system there's only two orthogonal, like two states, up spin and down spin. Those are the only two options.
Yeah. So, but there are different axes, right? So you can only
this kind of
measure.
Also comes from electron configuration as well, right? Because with half spin we're only dealing with the s orbital. That's why it can be up spin or down spin. So anyone who's taken grade 12 chemistry might know what I'm talking about. So in the electron configuration, the higher the configuration, basically, the more the possible up and down spins the electrons can have. But because we're only dealing with the s orbital, I believe, it's only the one or two. It's up or down in that one state, or in those two states. So
I was going to say that it depends on what you're measuring, right? Quantum mechanics has everything to do with observation and measuring, because everything is pretty much just unknown until you make a measurement. And that's why...
I think that's really cool.
Yeah, that's why
really cool.
When you look at the double slit experiment and you see this interference pattern, right, on the screen, you can ask yourself, okay, well, which slit is this photon going through, right? The one that, ends up at location X on the screen. You say, which slit has this gone through? Well, it technically went through both, because the reason that you see this interference pattern is because you don't know which slit it went through, right? If you put some type of measuring device where you can tell which slit the photon goes through, all of a sudden the interference pattern vanishes, because you basically collapse the probability.
We're going to talk a little bit about that later.
Yeah, so
the wave function can come a little bit later.
So you, by measuring where the photon comes from, you erase the uncertainty, right? So the photon came out of this slit, and so once you know that piece of information, it's no longer a double slit experiment. It's just a single slit experiment, right? The photon went through the one slit, and so the interference pattern goes away. All you see is just the regular like bell curve intensity distribution.
Yeah, because and this is where quantum mechanics, I believe, becomes super interesting. And I think we're going to talk a little bit about this, where the act of measuring something can actually change the state of the something that you're measuring. And I think that state, and I think that property in quantum mechanics is really what differentiates it so vastly from Newtonian mechanics. Because, for example, if I measure the speed of the car to be 5 meters per second, and let's say it's at constant speed, 20,000 years later, it's still going to be at 5 meters per second. The measurement will not change depending on when and how I measure it. But with quantum mechanics, when we're dealing with these subatomic particles, or these fundamental particles of nature that can be represented as mathematical waves, we're talking about all these different probabilities. And when we enter this realm of probability is when we see all these interesting things happen in quantum mechanics.
Well, I don't think that's actually completely correct what you said.
What?
Because if you measure, right, let's say the polarization of a photon, you measure it to be, let's say, horizontally polarized. 20,000 years later, that photon is still going to be horizontally polarized,
but what I'm
right?
saying, no. What I mean is the act of measurement can change the state of a quantum particle. Because when you measure it again, what I meant is when you measure what you measured first again, you will get the same result in classical physics. But in quantum mechanics, if you put, like, as you said, like a 45 or a horizontal through a 45, for example, and then you put it through a horizontal again, you will get both states. Seemingly, somehow, photons have arisen from a state that never existed in the beginning. How? Because of the measurement device in the middle. Right, so the measurement device seemingly changes the effective state of the quantum particle.
Mm-hmm. So to illustrate this a little bit... Yeah, to illustrate this a little bit easier, I think it's more intuitive to talk about photon polarization.
Yeah.
So when you think about light as a wave, you're probably asking, well, what is actually waving? You know, when I look at a light bulb, there's nothing that's going up and down or side to side. It just looks like the light is reaching my eyes and that's what I see. Well, actually, it's the electromagnetic field that is waving. So the electric field is waving, and then the magnetic field is waving perpendicular to that wave, right? But we can just talk about the electric field for now, just to make it simpler.
Because usually when we talk about polarization, we are in fact referring to the electric field, even though the magnetic field does play an important role, obviously, in making light, right? Mm-hmm. But we're mainly referring just to the electric part of the electromagnetic field.
Yeah.
When we're talking about polarization.
If you consider a light source like the sun produces randomly, or not randomly, unpolarized light, rather. Yeah. So there's no...
Or you can say randomly polarized as well, because it is polarized in like every direction.
Yeah. So when a light is unpolarized, it basically means that there's no particular direction that you'll find each photon waving in. And by when I say the photon waving, I mean the electric field, of course. Mm-hmm. So you can introduce something like a polarizer, right? Which has a direction. Right, you can have a horizontal polarizer, a vertical polarizer, and then a circular polarizer. Mm-hmm. Okay, so once you run unpolarized light through a vertical polarizer, everything that comes out of that polarizer is now vertically polarized with zero uncertainty, right? Yeah. So that's how basically you prepare a state. And this is analogous to preparing like a spin state. Let's say you want a group of spin up particles. You just have to sort them out, right? You run it through a quote unquote, spin polarizer, I guess. And then, or
a spin analyzer would be the better word.
Right. I was just trying to make allusion to the
polarization. I know. I understand.
So you run it through a spin analyzer, and then you just, every particle that comes out to be plus spin, you just have a collection of only plus spin particles. And if you remeasure the spin of those particles, it will always be plus.
Yeah.
Right?
Yeah.
So basically, same thing with polarization. If you polarize the light, it will keep that same polarization until, further disturbances.
Measurements are and this is where measurements and disturbances can actually be used analogously. I mean, this was perfect because we both used those different words, but they mean the same thing. Where a measurement can disturb the state of this photon, right? Mm-hmm. And I think that's or not this photon, but a collection of these photons. So polarization, I think, more realistic example can be talked about in the most realistic example of polarization, in my opinion. Polarizing sunglasses, right? Because the big problem with people wearing sunglasses, especially while driving, is the glare, right? And especially with snow or something bright there, when the sun reflects off of it, you get bright glare in your eyes to the point where sometimes you can't even see, right? So polarizing sunglasses are used by many, many people, and this is basically how they work. When the light from the sun hits, so glare works by reflecting things that... Sorry, let me rephrase that. Glare works by when the sun's light hits a surface and reflects straight into your eyes. What a polarizing sunglass, or what the polarizers do in your sunglasses, is it filters out all of the horizontally polarized light. And all of the horizontally polarized light is light that has hit surfaces and has come directly into your eye.
Right, so the reason,
polarizers...
Sorry, the reason why it filters out the horizontally polarized light is because when you have unpolarized light that reflects off of a surface, usually the light that gets reflected is polarized parallel to that surface. Mm-hmm. So let's say the sun is hitting the road in front of you, right? You know, when it's like the road is basically flat and it's hot outside, it kind of looks like water, you know, and it's really reflective.
A mirage.
Yeah, the mirage. So the bright light that reflects off of the road is going to be parallel to the road. So you're going to have horizontally polarized light heading straight for your eyes. So what the polarizers in your sunglasses do is that they're vertically polarized. So that the only thing that can get through your glasses is vertically polarized light. And so suddenly, magically, the glare goes away. And everything that is horizontally polarized, you just can't see it.
Yeah, and that's also a big advantage, I think we already mentioned, for driving, of course, where people use this also in the rain, where that's just sunglasses in the rain. I'm mixing up facts. I apologize.
What were you going to say about the rain, though?
Oh, I was basically going to say, so in the rain, if you wear sunglasses, and especially if you're driving, it filters out a lot of like the droplets. So if you're driving especially, and it's raining, it's heavily recommended that you wear sunglasses, even if it's dark outside. Because the sunglasses basically disturb the entire rain, all that water through it, because it makes your entire view darker. So you don't see those transparent water molecules. And basically, you can see a much better view of the road.
Oh, that's pretty interesting.
I mean, obviously, anyone can try this with any sunglasses and rain. And it actually works really well. So, highly recommended.
I've never actually tried that.
Yeah.
Yeah, so talking about polarization. Now, I hope as a listener, you have kind of an intuitive feel for polarization, right? If you're one, you can't be the other. So what happens if you have horizontally polarized light and you run that through a 45-degree polarizer with respect to the horizontal?
So right? What he's trying to say is, if you can like kind of imagine the Cartesian plane, I think this might be a nice way to think about it. Think of something on the x-axis coming along, even though it's not exactly true, but think of something coming along the x-axis, right? And you have a y equals x line, which is at 45 degrees, and you're trying to project that line that came through the x-axis onto the y equals x line. That's basically our idea.
Yeah, kind of. I think something that's important to note is that the electric field is waving along the x-axis, but it's going in the z direction, right? Like it's not going along the x-axis. It's propagating forward, but the electric field is going up and down the x-axis as time goes by. So, yeah, what would you expect to happen, right? If the light is horizontally polarized, it goes through a horizontally polarized filter. 100% of the light's going to go through. If it goes through a vertically polarized, 0% of the light is going to go through. So intuitively, right, if you have a 45-degree polarizer, you would expect that 50% of the light goes through. And that's actually correct. Okay? Ooh. But now, get ready to have your mind absolutely blown, okay?
Explosion soon.
So now we have 3 consecutive polarizers. The first polarizer is to prepare the state, and the next 2 are to blow your mind, okay? So first...
the next 2 are to blow your mind. I love that.
So the first polarizer prepares, let's say, a horizontally polarized set of photons, okay? Mm-hmm. The second one is 45 degrees with respect to the horizontal. So that means that half of the light gets through. The next one is vertically polarized.
Oh, what?
So now the light that comes out of the vertically polarized one, you see half of the half. So you get a quarter of the light going through.
Yeah.
Right?
Because
but
you sent it
hold
at
on 1
degrees.
second. Hold on 1 second.
Oh.
In the beginning, I had a horizontally polarizing filter. At the end, I had a vertically polarizing filter. But how am I still seeing light? If in the beginning we knew for certain that the light was horizontal, and then in the end we pass it through a vertical one, how is any of the light going through? And this alludes to what we said earlier, right? When you measure something, it disturbs the state of that thing, right? That particle. So the truth of the fact of the matter is that, yes, you measure initially a horizontal polarization, but the magic comes in with the second polarizer. Because once you measure a 45-degree polarization, you have no memory of what you were before.
Oh.
Right? Once you walk through that door of that 45-degree polarization door, you are no longer horizontally that passed through a 45. You are now a 45-degree photon. That is all you know. Right? Mm-hmm. And now you continue your journey. And now that you are a 45-degree photon, you arrive at the horizontal and you have another 45-degree angle with respect to the polarizer. Yeah. So instead of in the beginning having a 90-degree difference between horizontal and vertical,
we now have 45.
Now you just have a 45-degree difference. And so half of those photons are able to go through and half are reflected. And this just has to do with the fact that 45-degree, well, in essence, the 45-degree polarizer is in between vertical and horizontal. So that's why 50%
but obviously,
go through.
These examples that we're giving you is just a very specific, this will happen if this happens. But the interesting thing, obviously, of quantum mechanics is that this happens with almost every single measurement. Think about if we add another one, like a fourth one or a fifth one, or we add analyzers between some of them going up and down. So we take some of them that went down and do something with that. So there are countless, almost infinite options here with these polarizers and analyzers that we can take and see all these weird quantum effects taking place. Also, one thing I did want to mention, the thing I was talking about before, when I said sunglasses in the rain, what I was thinking of was skiing glasses. I don't know why I mentioned sunglasses, but anyways, I was actually thinking about how ski goggles, or at least the polarized ski goggles, are, yes, very expensive, but very recommended for, professional skiers. Why? Because it reduces glare. You'll actually be able to notice if you do ski and you're not wearing polarizing goggles and the sun is crazy. You'll be able to, the only way to ski down the hill will be to squint your eyes because you have to reduce the glare. But the polarizing sunglasses or the polarizing ski goggles do it for you in this case. So polarizers are used almost everywhere.
That's awesome.
In nature, in reality.
So also I wanted to say that a lot of people think that quantum mechanics is really it's this weird realm where magical things happen. Yeah. But an interesting thing about the experiment that I just described is that you can go on Amazon, buy some polarizers, and see for yourself. Yeah. You can actually, it's not even that expensive. It's probably $20 to buy a couple polarizers. And then you can see that you do horizontal to vertical, nothing gets through. It's just completely black. And then you stick another one in between at a 45-degree angle, and suddenly, by adding a polarizer, you can see more light. Which, it's a quantum mechanical experiment that you can perform in your bedroom. So,
and the interesting thing that this also tells you about the light is that the light only depends, so where it will go only depends on the relative angle between it and the polarizer. It does not depend, as Parker very well mentioned, on what it was before. It seems as if it forgot or lost memory of what it was before. But another way to think about this, like, more mathematically or more in the physics sense of it, is that the photon, or in this case the light, only depends on the angle relative to which it is left and which it is going through. So the moment the horizontal turned into the 45, as Parker said, it forgot about the horizontal. And now it's a 45. So the only thing that matters is the relative angle between it, which is now 45, and the vertical, which is also 45, the relative angle. So because it's 45, there we get the 50-50. And that's basically where this crazy confusion and interestingness of quantum mechanics comes out.
I think it's really sad that quantum mechanics is so mathematical, and it's one of the reasons why so many people just don't even bother learning quantum mechanics.
That is true.
Because, you only really start learning about quantum mechanics in, a university quantum mechanics course. Like I had a quantum mechanics I'm just gonna say QM from now on because that's just a long word. But QM. Yeah. So I remember the QM unit in high school was complete trash. Like, it was so bad because, in part, because what can they really teach us? We just know grade 12 physics. They can't really explain it to us mathematically because we just won't understand anything. We didn't even know integrals in grade 12. So. So I'm not saying that's an issue. I'm just saying it's a fact, right? So
it's just that quantum mechanics, to really understand it, just simply requires a little higher level of math, because the only way to truly understand what a state is with bracket notation, right? To truly really grasp it and how to multiply it and how it goes through states, bracket notation really helps. But how do you learn that? You learn that mainly with a lot of advanced mathematics, with linear algebra, functions, with a lot of calculus. So it all kind of adds on to itself to put itself on this pretty high pedestal where it needs so much math to function that so many people are afraid of it.
Yeah, mainly I think it's pretty much all linear algebra, to be honest.
Yeah, it's a lot of linear algebra.
There's a lot of concepts where it just has to be kind of just natural to you for you to succeed, quote unquote succeed. Just being able to, analyze a situation correctly, and just instead of thinking about the situation for what it is, you think about it more mathematically and analytically, and then etc.
Yeah.
I also wanted to say something about an experiment that we did in class, but I think
the Michelson-Morley experiment, or interferometers. We can talk about interferometers.
The interferometer.
Okay, one thing. I definitely do want to mention. So, for people who have not heard of an interferometer is a very, very interesting piece of equipment, or it's more of an experiment where light. Or do you want to explain the interferometer? Because I really want to explain LIGO.
No, go ahead.
Okay, perfect. So an interferometer is basically a device where light is sent out from, there are many different types of interferometers, but in this case, we can say light is being sent out from a singular source. And an interferometer is basically a mirror in the middle of these sources where the light is traveling to split the light into two separate polarizations, into a perpendicular polarization and a parallel polarization. Then, when the light splits from the center, it hits either a detector or a reflector. Usually it's mirrors, because that increases accuracy of experiments, and I can talk about that later. But usually it's mirrors, and the light basically can bounce back and forth n number of times till it comes back to a certain detector. Now, the interesting thing about this experiment is that, remember, the one light got split into two separate beams. So both of those lights, when they return to the detector, have a certain interference pattern. And that interference pattern is how we can measure something extremely interesting. So LIGO, and this is really where I want to come into it. So LIGO, the Laser Interferometer Gravitational Wave Observatory, is a huge experimental apparatus with arms as long as 4 kilometers, I believe. Very, very, very long arms. Definitely recommend, search it up. Where the point of it is, it's basically an interferometer. It is an interferometer. And the point of it is to detect gravitational waves. Now, gravitational waves, which we have spoken about before, I believe, are small ripples in space-time. But we can't really measure them with anything that we have today. So we need this equipment with such level of precision where we can measure if light that's bounced around hundreds of thousands of times moves just a little bit. Let me explain. So in LIGO, the default configuration is that both the light, the perpendicular component, and the parallel component, when they come back to the detector, they have destructive interference. That's the point of it, right? So that you basically can't see any light at all. However, the moment a gravitational wave or something that ripples through space-time hits this light, it will hit the parallel component in a different way that it hits the perpendicular component. This will cause an interference pattern between the perpendicular and parallel components of the light. So when they hit the detector, we detect some light. What this tells us is that a gravitational wave has just passed through. So in 2015, interestingly enough, when they had shut off the observatory for 3 years, they just started running it. And I think a few months later, they caught the first glimpse of a gravitational wave, thereby proving Einstein's general theory of relativity. And I think this is where I could really talk about LIGO, because I wanted to talk about it before so much. But because we're talking about interferometers and polarization, I just feel like this is the perfect spot. So yeah, I know it took a little bit of time explaining that, but I think that's a really cool thing. And if you guys have time, definitely search up LIGO. It's really cool.
Yeah, so one thing that I just remembered while you were talking is that in our astronomy class that we're actually taking together, Ray and I, we were talking about nuclear fusion in the sun. And we ran through a couple of approximations that told us how hot the sun should be based on the nuclear reactions happening inside of the sun. And we got a number that was too low, I believe.
Right?
Yeah, it was like 10 to the 3 kelvins less than the actual temperature at in the middle of the sun. And so our teacher was like, "Hey, well,
no, sorry. Little thing here. It's 10 to the 3 Kelvin less than what it should have been for nuclear fusion to occur." You said than the temperature at the core of the sun.
Okay, right.
Yeah, anyways. Sorry, just small correction.
Yeah, you're right. So, yeah, basically they were saying, okay, so the temperature of the sun is not hot enough for this level of nuclear fusion to occur, right? So what they actually, the solution to this problem was you need to consider quantum mechanics. You need to consider the uncertainty principle, and that every subatomic particle has a wavelength. And so you don't actually have to have this impeding pressure forcing the actual particles to touch. All you need is that the particles have to come within one wavelength of each other. And because you have that uncertainty, then, sometimes what will happen is that they will interact with each other without ever really touching each other, quote unquote, touching each other. And that's where nuclear fusion occurs without actually needing the proper temperature / pressure for, classical nuclear fusion to happen inside the sun. So I found that really interesting how we needed quantum mechanics to explain things that are happening inside of the sun.
And the formal name for the effect, for the process of what's happening, is known as quantum tunneling, which I believe we also have covered before. And I think this we spoke about in part 1.
I think we did, actually.
Yeah, I feel that we have spoken about, where
because we mostly talked about like things we saw in first year quantum, which wasn't
So quantum tunneling is what allows. So when these particles are within one wavelength of each other, the advantage is that these particles can just tunnel to each other and then fuse that way.
Yeah, so, I mean, I think we've covered a lot of material up to now. I hope everybody has taken something away from this podcast, whether it be like polarization or something cool, a cool fact about nuclear fusion in the sun.
Yep.
We love talking about quantum mechanics always. It's a beautiful topic conceptually and mathematically. If you want us to do a part 3, which we will definitely do, if not sooner than later,
for sure.
Just let us know. If you have any questions, make sure to email us or follow us on our Instagram page, which is at math.physics.podcast. Other than that,
you can email us as well. Did you?
Yeah. So the email is going to be in the description of the podcast. It's uoft.math.physics@gmail.com. Also, very last thing, make sure to follow us. We are on the climb to 1,000 followers on Spotify. So if you're listening to us on Spotify, make sure to follow us. Awesome. If you've made it all the way through this magnificent episode of mathematical and physical discussion, we hope you enjoyed this episode. This was
thank you so much.
Yeah, thank you for listening. This was number 29. We are close to 50 episodes.
Yeah, I was just gonna say we're closer to 50.
Yeah,
I think 50 is gonna be a big mark.
Actually, I think 52, because that would mean like an episode per week. That's like a year. I guess,
but if you remember in the beginning, we weren't doing an episode.
We did post more than.
Yeah, we did post more. We posted more.
Man, back when we had time to post twice a week.
Now we just don't.
Now we're recording 12 hours before before we have to post it.
Yep.
All right. So, yeah, I hope you enjoyed. Do you have anything else to say, Ray?
Not really. Just I kind of got cut off there for a second because my my cable came out, so my mic disconnected. So I think you just began talking though. So I'm not sure if people heard that.
All right. Well,
that's all I have to say.
Okay, we will see you guys next week.
See ya.
This has been the Math and Physics Podcast with your host Parker,
and I'm Ray, and we will see you soon.
All right, peace out.